This video will talk about auto transformation of high-level language software to Verilog, a hardware language. This is the first video in a series of videos that we will discuss about conversion of complex software programs to Verilog for hardware acceleration. You can find the video at this link. The focus here is C to Verilog. So why would you want to do such transformation? One reason is to accelerate the performance and the latency of software using hardware. Code that are data-intensive, scientific computing, or math-oriented functions are prime candidates for hardware accelerations. The same code running on hardware such as FPGA or ASICs would be faster, low power, and maybe more secure than the software equivalent, and a huge code base available that can benefit from this method. In terms of methodology, our interest here is mainly from very high level software be able to convert it into Verilog, and from Verilog can be implemented in FPGA or ASIC. And to go from high level software to Verilog, we will first go from high level software to C, and then from C to Verilog. So the C code is an intermediate representation. It's a reference code between the high-level software and Verilog. C can be used for auto-verification purposes or be kept as for documentation, or it's really an artifact that you can use for quality control purposes. If you reiterate the process, you can use it for comparison between runs or quality control method. Verilog to FPGA is well known, and there are several tools that available commercially or open source can be used. C to Verilog tools are also available commercially, and very few is available in open source. This first video is about C to Verilog demonstration, and the next video will be from very high level software language to C. C2V tool. For commercial tools, they are available from different FPGA vendors. For example, you can see the Vitis tool from Xilinx or the Vivado high-level synthesis tool. The open source tool, there are very few. One of the tools that we're using here is called Panda or Bamboo from Politecnico di Milano. And they give us a very good support during our testing process, so we would like to thank them for that. For the demo, we'll use simple counter, and we'll show you some code walkthrough. Then we will use more complex code segment from our LDPC error correction code with matrix operations, and we will compare the C output to the waveform that we gather from the Verilog simulation. And in simulation, we use the matrix add, multiply, and transpose. Some interesting observations. The code can be completely optimized away if the output is not explicitly used, and it will optimize away by the tool. The tool does use memory in an optimized way. It can store multiple matrices in the same memory location index. So by reading one memory location, you can get two values from two different matrices, for example. It depends on the size of the variable. So it does some parallelization for performance purposes. It also reuse memory location for calculation and storage, so it saves memory and register space. But this area can be enhanced for better synthesis in terms of frequency. By reusing the memory, it will save memory, but it may not be the best thing for frequency. For complex data structure and code sequence handling, Most of the tools are able to handle array quite well. If you have pointer to an array is really represented by a pointer, so it treated as a pointer to a pointer, and some of the tools may not be able to handle it. More complex things like recursive function calls, this is generally not done in hardware, so we don't expect the tool to handle such capability. In terms of code readability, the commercial tools do seem to have better code result for readability. The code generated by open source tool, it is readable, but it would require some analysis from the human. In general, the figure that you see on the left-hand side here is the structure generated by the tool from C to Verilog. And inside the Verilog code, you will see a controller, which is a state machine, and some combination of logic or data path. Data path is like add function, for example, and combination of logic, maybe mux and things like that. And the combination of the data path take input from external or from memory that are predefined. The controller state machine take input from a start control signal and also reset and clock, of course. The output of the controller and the data path are buffer for synchronization. And for example, the done signal is being buffer before it's sent out. And if your code required some result to be returned, it also generates that. The controller state diagram is interesting, so we'll explain that a little bit. It has an idle state S0, and when the reset happens, that's the state that it go into. And when the start signal is given, then it moves into state S1. It contains one or more of these states to do the processing. And during the processing, if it hit the condition for exit, for example, if you exit a loop, then it go to a pre-done state, and in pre-done state, it generates the output control signal called done. Then it go into an end state, and then from the end state, then it go back to the state idle. So in the next part here, we will show you the actual code running on a demo.
I'm going to show a demo of a Panda tool which converts C program to Verilog code. In this demo, I'll be using two C programs. First one is of simple counter, as you can see right now, and the second one is of matrix addition, transpose, and multiplication. So I have a counter function which increments the count value by 1 every time, and if my count value is equal to the end value, which is 50, it will simply return the final count value. Now let us convert this C program to Verilog. So the command to convert this C program to Verilog is bamboo. The file name, we have to instruct that we need to simulate, and the simulator that we want to use, it will generate the VCD file and accept non-zero return. So as you can see, the total number of flip-flops created were 45, and total cycle for simulation is 53 cycles. Now let me show you the Verilog file that it generated. So this is the Verilog program that was generated by the tool. It has the input as clock, reset, start port, and output as return port, and there are various submodules also. Now let us see the output on the waveform. So I'll just show the waveforms on GTK wave. Now I'll pull up the signals for main program. Here, as we can see, this is the output as written port, and we get the final output as 32, which is in hex, and if we convert that to decimal, it's 50. Now if we want to see the incremental values of counter in each clock, we need to pull up the signal from its data path hierarchy. So I'll just pull up one signal, and here you can see that in every clock we are getting an incremental value starting from 1, 2, 3, 4, and it goes so on till the end, that is 32. And once we get the done port, we output our final value to the return port, which is the output port of the main module. Thus I showed the C2 Verilog code of a counter. Next I'll show you the code conversion of matrix addition, multiplication, and transpose. This is my code for doing the matrix addition, multiplication, and transpose. In the main function I have some matrices pointer, and mod to dense allocate function allocates a matrix. This is the row and these are the column number. Mod to dense set function sets the one at different locations in the matrix. And as you can see, I'm using a mod to dense transpose function to transpose the M1 matrix to M4. Next, I'm allocating 3 input matrices and there are 2 output matrices, and mod to dense set function is used for setting the bits to 1 at different matrices locations. And then in the end I'm using mod to dense add function to do the addition of S0 and S1 matrix, and the result is stored into S4 matrix. Similarly, the mod to dense multiply function is doing multiplication of S1 and S2 matrix, and the result is stored in S3 matrix. Now let us convert this code into Verilog. So as earlier, the command to convert C program to Verilog is using Bamboo. The file name simulate simulator generate VCD and accept non-zero return. And as you can see, there are number of print messages on here which provides the information about the number of modules instantiated, the estimated area, and the total number of flip-flops, which in this case is 1483, and the total cycles it took for simulation is 2332. Now let me show you the Verilog code that is generated. So here a main module, which is the top module, is generated, and there are several sub modules as earlier. And I would just like to show you the instantiation of different functions. Here mod to dense add function is instantiated, and also the mod to dense multiply function is instantiated, and the mod to dense transpose function is also instantiated. Now let us see the output on GTK wave. So as shown, I'll just pull up the signals of mod to dense add function and mod to dense multiply function. As we know, the mod to dense add function was initialized as FU main 2670828812, and here also we are pulling up the signals of that same module. Now the output is in the M out W data RAM, and the valid output is given by M out W RAM. Just zoom in a little. So this is my first output, and I have also simulated the C program just for the reference. So our S0 matrix is this one, and S1 matrix is this, and the sum of the matrix is shown here. Now the input to this matrix are shown here. The first column of matrix S1 is in the upper 32 bits of our data RAM, and the first column of matrix S0 is in the lower 32 bits, and the result of 8 plus 4 is C as shown here. And next we move to next column addition. So here the input is 1 8, as you can see here, second column, and the input is 8 for S0 matrix. So 1 8 and 8, and the result is 1 0, as can be seen here on the second column. For the third column, the inputs are 0 and 1 1, and the output is 1 1 as well, and we can see that the output is 1 1. For the fourth column, it's C, the output is C, and we can see here the output is C, and it is written at this memory address. The result for fourth column is 1 2, and as we can verify, this is 1 and 1 2. Similarly, the output of fifth column is 0E, and the output of last is 0A, and as we can see here, thus the matrix addition is done correctly. And if you see the memory locations, it is also in incremental fashion, so every column is stored in the memory at the incremental address. Next, I'll show you the output of multiplication function. Here the multiplication is done in step-by-step process. So every time the previous intermediate value is overwritten at the memory location and the new value is written. So just to understand in a simple manner, I have created a table of the output values. So here we can see that the output value at memory address 208 is 08, and I can show you here. So the first output is 208, and then the second output is written at address 20C, which is 18. So 20C 18, this is the intermediate result. Next, again at 20C, the output value is written as 1E, which is this one. And here at location 210, the output value written is 06. And location 214, this is the intermediate result, which is 0E. And again, this is the intermediate result, 1E. This is the final result as 18, which is written at 214. Now at address 218, the intermediate result return is 0E, 1E, and the final is 1A. So the final values are at location 208 is 0 cross 08, at location 20C is 1E, at location 210 is 06, at location 214 is 18, at location 218 is 18. Now let us compare this with the output of our C code. So here this is the input matrix S1, and this is the input matrix S2, and the product, first column product is A, which is written at address 208. The second column product is 1E, which is written at 20C. The third column output is 06, which is written at 210. The fourth column output is 1,8, which is written at 214, and similarly the output of fifth column is 18 as well, which is written at 218. If you see, the address is incremented by 4, 280C, 210, 14, and 18. Thus the output of the multiplication is correct as well, and we verified that on the waveforms. Next I'll show you the output of a transpose function. Here also the output is written in moutw data RAM. As you can see over here, in the transpose function as well, the output is given in step-by-step process. So let me take you back to the PDF that I created. So here at address D8, the first value written is 000. Next, at the memory location DC, the value written is 000. Next, at location E0, the value written is 000. So this way the intermediate values are written at the memory location, and it overrides the previously written value at that same memory address. And as you can see, here at memory location D8, this is the last value that is written, which is 17. At memory E0, the last value written is 1C, and this is the final output that we get for our transpose function. Now let's compare this with the C output. So here the input matrix is 3 by 5, and this is the transpose of our input matrix. As you can see, the first column output is 17, which is written at memory address D8. The second column output is 0B, which is written at DC address, and the third column output is 1C, which is written at E0 address. Thus I showed you that we converted the matrix addition, multiplication, and transpose C program to Verilog, and we verified the results through waveform and also through the C program.